You know, for as long as we've been around, we've been trying to fix ourselves when we break, replacing worn-out parts of the human body, almost like a mechanic fixing a car. And the history of medicine? It's just littered with these attempts, from wooden pegs to iron plates, all trying to mend our skeletons. But as it turns out, putting anything foreign inside of human body is incredibly tricky. Today, we're going to talk about the one metal that really changed the game: titanium. And this image right here, this is the whole challenge in a nutshell. On the left, you've got a natural hip joint. It's an absolute marvel of biological engineering. And on the right, it's high-tech replacement. The entire goal of modern medicine here is to bridge that gap, to make that replacement so good that the body doesn't just tolerate it, it actually accepts it as part of itself. This is where it all starts. All right, so before we get to our star material, we have to understand the problem it was born to solve. Because for a very, very long time, putting any kind of metal inside the body was a massive, massive gamble. Now, what's fascinating is that the inside of your body is just a terrible place for metal. I mean, think about it. It's warm, it's wet, it's basically a saltwater bath full of corrosive chemicals. So those early metal implants, a lot of them made of stainless steel, would just start to corrode. They'd turn out to be way too weak for the day-in, day-out stress of just walking around. And yeah, in some cases, they would literally just snap. Not exactly what you want from a hip replacement. So all those failures led scientists to create this kind of holy grail checklist for the perfect implant material. First, it needed ductility. That means it can bend a little under pressure instead of just shattering. It obviously needed incredible strength to handle a lifetime of movement. It needed the perfect stiffness, not too rigid, but not too flimsy. And the big one, the most important one, biocompatibility. It had to be able to play nice with the body. And this is where our hero, titanium, enters the story. It's a metal that for a long time was mostly found in stuff like fighter jets and spacecraft. But when researchers started testing it, they realized it checked off pretty much every single box on that implant checklist. Okay, let's just lock in on this term for a second. Biocompatibility. This is so much more than just being non-poisonous. It means your body's incredibly complicated immune system doesn't look at this thing and see a hostile invader. It doesn't launch an all-out attack. The implant has to be like a quiet, friendly neighbor that just keeps to itself. And this is where titanium does something that honestly sounds like science fiction. It achieves something called osseointegration. It doesn't just sit next to the bone. Your living bone cells actually grow onto and even into the surface of the titanium, physically locking the implant into your skeleton. It's not just a replacement part at that point. It literally becomes part of you. So what's the secret? How does it do this? Well, it's pure chemistry. The second titanium is exposed to the air, it instantly forms this incredibly thin, super stable, and chemically non-reactive layer of titanium oxide all over its surface. It's like an invisible suit of armor. And that layer is what your body actually touches. And because it's so inert, your body's cells basically don't even know it's there. It's the ultimate stealth technology for medical implants. So, we know it's a good neighbor, we know it's stealthy, but that's just the beginning. Let's dig into the specific mechanical advantages that make surgeons love this stuff so much. This chart just lays it out so clearly. You compare it to the old standard, stainless steel, and right away you see titanium alloys are way lighter, which you definitely appreciate. Their corrosion resistance is off the charts better. But that middle row, elastic modulus, that's the real magic. It's basically a fancy term for stiffness. And this right here is the game changer. You don't want a totally rigid iron bar inside a flexible skeleton. Because titanium's stiffness is so much closer to actual bone, it can flex with your bone. It works together. And that synergy doesn't just feel more natural, it can actually help the bone heal better around the implant. Let's just put a number on that. Titanium alloys are about 50% less stiff than the stainless steel used in medicine. That is a massive difference, and it's totally key to creating an implant that works with the body, not against it. But, you know, like any hero in any story, titanium has a weakness. It's not perfect. And it's really important we understand the downsides that engineers are still trying to solve today. And here is a huge paradox. It's a phenomenon called stress shielding. So your bones need stress to stay strong and healthy. It's that classic use it or lose it principle. But if an implant is too stiff, it carries most of the load from walking and moving, effectively shielding the bone around it from that healthy stress. And what happens to that bone? It can actually get weaker and start to waste away over time. Now for the elephant in the room. The most common medical-grade titanium isn't pure. It's an alloy, and its name is T6Al4V. That name is literally its recipe, titanium with 6% aluminum and 4% vanadium. And those two additives, well, they've started to become a real cause for concern. So even though the alloy is incredibly stable, over many, many years, tiny little ions of these elements can leach out into the body. And here's the concern. Vanadium is known to be cytotoxic, meaning it's toxic to living cells. And some studies have raised red flags about long-term exposure to aluminum and potential links to neurological problems. That potential risk is what sent scientists scrambling to find safer ingredients for the recipe. Which brings us to a question that sounds kind of crazy, right? Could your own immune system actually turn against the very device that's supposed to be helping you? Well, the answer, for a small number of people, seems to be yes. It's called metal hypersensitivity, and it's a very real thing. The science is still developing, but we know some patients can develop immune reactions to the metals in their implants, which can cause pain and swelling and all sorts of complications. It's a really tough problem to diagnose. Okay, so we've got this amazing material, but it's got some serious flaws. But this is where the story gets really, really exciting. Because science isn't just standing still. Engineers are actively building the next generation of bionic materials, right now. Check this out. This chart basically shows you the whole family tree of medical titanium. We started with these simpler alloys, then we moved to that workhorse in the middle, T6Al4V. But the real revolution is happening at the bottom, the beta alloys. These are a whole new generation designed specifically to solve the problems we were just talking about. They're safer, and their stiffness is an even better match for our bones. And what makes them safer? Well, they've kicked out the troublemakers. They've replaced the aluminum and vanadium with elements that we know are incredibly biocompatible, things like niobium, tantalum, and zirconium. This is the future, getting all the strength of titanium but with none of the potentially toxic baggage. But the future isn't just about better chemistry. It's about smarter design. Look at this comparison. On the left, a traditional, solid implant. On the right, the future. These incredible, intricate, porous structures that look almost like bone themselves, they're made possible by one technology, 3D printing. Yeah, additive manufacturing or 3D printing, it changes the game completely. Now surgeons can print custom-fit implants with this precise, porous lattice structure. And this design, it doesn't just let bone grow onto the surface, it encourages the bone to grow through the implant, weaving it all together into one unified, living structure of bone and metal. It's the difference between just placing a brick on the ground and actually building it into the wall. And this really leaves us with a pretty wild final thought. We started this whole journey talking about these inert chunks of metal that were just meant to prop up our skeletons. And now we're engineering porous, bioactive structures that truly become living parts of us. And as these bionic parts stop being simple machines and start becoming integrated biology, well, that old clear line between human and machine starts to get pretty blurry.